This is the AMC12 problem that only 1% can solve. It is a simple equation. However, it is savagely difficult. But today, after you watch this video, you will learn how to solve this independently by yourself, because it, with logic, is not all that hard. So when we come down to solving equations and inequalities, which is the fundamental thing of algebra, there are three things that we should talk about. The first is solving for x, which is essentially what most people think equations are all about. That is incorrect. This is only the basic part of equations. When we move up one step, we then learn what to solve, which is the so-called equivalent amount. And then finally, in the end, we learn to what extent do we solve. Combining these three, you can solve basically any problem. However, the problem that I just showed is a problem of pure elegance, of difficulty. It does not require your complex understanding of this three-step equation. So there is a fourth step, which is breaking down equations. However, luckily, you have already learned how to break down equations, which is dissecting constraints. Yes, that is correct. Then why do we learn the second step and third step to reach the ultimate step so that we can solve our problem? Well, let's dive in together, and by the end of the video, you probably understand why, unless you have a systematic understanding of equations, then you can only solve the ultimate problem. Now, you might be saying, there is a second part to the topic, inequalities. What about that? Well, inequalities is simple. Equations are of the form something is equal to zero. Inequalities, on the other hand, is solving where something is less than or greater than zero. Then basically you just have to solve for equal to zero, then convert it to negative or positive. We'll go into that deeper later. To begin with, let's extend our knowledge on solving basic equations. First of all, we already know how to solve linear equations of the form ax plus b is equal to 0. The solution is simply x equals negative b over a. For quadratics, of the form ax squared plus bx plus c equals 0, the solution is x equals negative b plus or minus, there are two roots, b squared minus 4ac under the square root mark, and then finally over 2a. This I expect you to know by heart. Apart from that, there are also techniques like formulas. I listed some formulas below in the description where you can check the material. There's a link you can consider remembering, even though they aren't all that important. But the ultimate goal of formulas is, in fact, factorization. This is the third and the most important way to solving general equations where there are only powers of x. For instance, if we have a third degree equation, if we can write it into the form of x minus something 3 times, then we can obtain all three roots. Because for this equation to be 0, one of the three terms of the product must be 0. How then are we to factorize? By which I mean generally. Let's consider this in the reverse fashion. Suppose we have a root x equals p over q. This can be written as qx minus p is equal to 0, right? Now, since this must be a term in the factorization because x is a root, suppose we have other terms here. We don't know much, but after we expand the left-hand side, there's one thing that we do know. The coefficient of the highest term of the right-hand side must be a multiple of q. Similarly, p must appear in the constant term. That is, p must divide the constant term. Of course, in both cases, I'm referring to the coefficients being integers. That is the only requirement. Given this, you can perform what is called root guessing. Let me show you an example of what root guessing is. For this equation over here, we can guess the root x equals 1, which can be written as 1 over 1. So 1 in the numerator can divide 3, 1 in the denominator can divide 2. That means this root is possible in the first place. Suppose this equation, the left-hand side, is polynomial p. then we notice that since we guessed the root 1, P1 is in fact 0. That means x equals 1 is a solution to the equation. Similarly, we can guess x equals 3 over 2, because 3 divides 3 and 2 divides 2. So again, if you can verify this, you will realize that P3 over 2 is in fact, again, a solution because it is 0. Similarly, you would obtain the solution x equals -1 as well. With that, you of course can factorize this into the following expression. Now, this can be a little bit difficult because you have to guess 3 times to obtain all 3 solutions. Then how can we reduce them a little bit? First, guess whole numbers, where the denominator is simply 1. Then you can try to guess fractions when it gets desperate. But the reality is, after we successfully find one root, we know that this part, even though we do not know exactly what the factorization is, we know this is already a quadratic. Then we can do long division. This. You can simply do long division just like integers. You try to remove the highest term each time. In this case, let me just demonstrate how you can go through long division. And we are done. In fact, 2x squared minus x minus 3 is simply x plus 1 times 2x minus 3. Now, of course, there is a fourth technique, substitution. For example, in this case, we can substitute a equals x squared. Then the original equation becomes this, which is factorizable because it is simply equal to a minus 1 times a minus 2. Since it is equal to 0, a is equal to 1 or 2. Therefore, x is equal to negative square root of 2, negative 1, 1, and square root of 2. And we're done. Similarly, this problem also requires substitution because this is not a standard polynomial that it is easy to solve using root guessing. Try it yourself. Now we are encountering an inequality. As I mentioned, we first solve the equation. Well, the equation we have already solved. The roots are negative 1, 1, and 3 over 2. This, in my opinion, is a great way to represent positive and negative because over here this is equal to 0. The upper region is greater than 0. The lower region is less than 0. Now, consider a point somewhere located over here. Where should the point be projected to? The greater to 0 part or the lesser to 0 part? Well, we can write this in factorized form, which is this. Since the red point here is less than 1, so all 3 terms of the factorized version is less than 1. So it should, in fact, be projected to somewhere below the central axis. Similarly, you might notice that some point over here will be projected upwards to the positive region, and again downwards to the negative region, and upwards to the positive region. So if we connect this, we obtain something like a graph. And that means this section is always negative. This section is positive, this is negative, this is positive. So the solution to our inequality is the following, represented on the number line. And a quick note on sets and set representation. I recommend you to just ask ChatGPT yourself. But if ChatGPT isn't supportive for you, then you can ask me down below in the comments section because I won't cover sets in this series because personally I think it's just something quite simple that is not really problem solving. It is really just a technical way of making representation easier. So for example, in this case, the way I would write the solution in a very standard way would be x belongs to the interval negative infinity to negative 1 combined with 1 to 2, 3 halves, not inclusive. This is the solution. You can check it out what this means after this video, okay? So we're basically done solving basic inequalities. However, sometimes inequalities can be a little tricky, especially when a parameter appears. And here I'm just going to give a brief explanation of what you can do when parameters appear, and that is special values. For this case, plugging in t equals 1 or -1, we obtain two different equations, and combining the parts, which satisfies both equations, you can solve for x. However, this is not always true. And in the fourth video, I will give you an easy way to justify why this is true, and similarly why sometimes it is not true. So the solution of this problem, I would write x belongs to -infinity to -2 inclusive combined with 2 inclusive to infinity non-inclusive. This is the solution. You can check it out later. So now we're done. In the first phase of our lesson, we have successfully solved the basic equations. Now we are to bring our equation solving ability into problem solving and solve equations that originated from problems, which requires us to know what to solve. For instance, this. Let's see if we can find the equivalent amount. And once you see the equivalent amount, you would probably know what I'm referring to by the equivalent amount. Okay, keep this in mind. For this problem, this simplifies down to, and a, b, c are integers. So try to solve this for yourself. So what you probably did here is you removed n and only focused on the exponent. And that is in fact correct, because this is in fact the equivalent amount. And then what do we do from here? First, notice that the inside 1 plus 1 over c is simply c plus 1 over c. So this is some useful information because this decides whether it can be solved. Let's then move the a over here and remove the 1. So if we organize it a little bit, it looks more or less like this. Since a is greater than 1, so we can first try a equals 2. This leaves us with a right-hand side of 14 over 36, which is 18 over 7. Then we can try different values of b. However, recall that c plus 1 over c must be what is left when we multiply both sides by b. So it is quite obvious that the numerator then should be 6, so b must be 3. That means the answer is a triple to 3, and in this case, c is equal to 6. And we are done. This is a classic difficulty 3 problem in AMC12, and even if I'm explaining it out loud, it still doesn't take way too long. So it isn't too hard, don't worry, you will get onto the track of problem solving very easily. So you can read the problem first. In the meantime, I'm just going to summarize the problem. And in fact, it is essentially asking you ln of n plus 1 times n plus 2 over n times n plus 3 is equal to ln 91 over 90. What is n? And in case you're wondering what this guy is, ln, well, you can just treat it as a function where x must be greater than 0. Pause the video and try. The way to go here again is just to ignore the function. We just don't care about this thing, and we solve this. Well, this is a quadratic, and solving it gives n equals -15 or 12. 12 is the only possible solution where x is greater to 0, or in this case, n is greater to 0. So the answer is 12, and we are done again. Again, not hard. Another difficulty 3 problem. That is basically the equivalent amount in a simpler version. But now let's examine an example which is far harder, a difficulty 4 problem. Let's examine this closely, and you can try it yourself first and tell me what is k. Well, I hope you took a try, and now I will guide you through the problem solving process, and let's see what we can arrive at here. So first of all, if we examine the constraints, there is actually something special, which is this. And in fact, there is a way to solve this problem elegantly. However, I'm going to go by the less elegant way, where we are going to do some more intuitive analysis of the problem compared to algebraic analysis of the problem, because really I want you to focus on finding the equivalent amount. Okay? So in this case, we're first going to move the denominator to the right. That gives us a left-hand side of 2 to 289th power plus 1. The right-hand side then is the original sequence of powers of 2, and then also the sequence that is multiplied by 2 to the 17th power, or we can write it as this. And this is more or less sorted. By more or less, I mean this term can be plugged into somewhere of the first segment, where we call this the original part. And the added part in the back, well, each part is sorted, but this thing can be smaller than one of the a2 to the a something's power. Okay? So this is important to keep in mind, the reason of which is because there's a very cheeky little term over here, 1. The 1 can only be obtained by concluding a1 equals 0. Because if a1 is greater than 0, then the right-hand side is an even number, while the left-hand side is an odd number. So a1 must be 0. That means we can replace these two with 1 and 2 to the 17th power, where 1 can be cancelled off. Then we are now to analyze the rest. So since this looks really like a binary number, we can treat the left-hand side as a binary string. There are a total of 289 zeros here. Meanwhile, the right-hand side is also a binary string. However, we do not know the majority of the string yet because we don't know what exactly the terms of the sequence are. But we know at the 17th digit, there's a 1 because we have 2 to the 17th power up there. And now let us think about how can we construct the right-hand side so that it is equal to the left-hand side. First of all, there is no 1 at digit 17 of the left-hand side. That means carrying must have existed. So here there must be a 1 also on the 17th digit. Then this means the 17th digit then becomes 0 in the end. However, this gets a new digit because of carrying. That means here you must also add another digit on another 1 on the 18th digit, so that the 18th digit becomes 0, and you get a carrying 1 from the 18th digit to the 19th digit, etc., etc., etc. Essentially, what the conclusion here is, basically, in the end, the string is just going to look like something like this. Here, this is the 288th digit, and if you add the string up there, of course, there's zeros at the end. If you add these two strings together, you would get the left-hand side. That means we must place exactly 272 ones from the terms given by 2 to the a2 to 2 to the akth power, and 2 to the a2 plus 17th power to 2 to the ak plus 17th power. This is what we require. For every single a, it is going to contribute 2 ones because there is an A2 and also an A2 plus 17 in the list, right? So if we want to contribute 272 ones in total, that means we must have 136 terms starting from A2 to AK. And since the first term is 0, that means K then must be 137, and we are done. This is, in my opinion, a really intuitive and clear way of analyzing the problem compared to some algebraic analysis, which we might do another day. But in this case, this is, in my opinion, already a great way to solve it. So we're done with this difficulty 4 problem, and I bet it isn't too hard for you, and I hope it is still clear. Okay? So in case you have any problems, be sure to ask below, because asking is such an important part of learning. Now, we have basically demonstrated what to solve is, right? So now we're supposed to move up the pyramid again and analyze to what extent do we solve. Again, you can read the problem yourself, but I'm going to skip the problem reading to save time. Essentially, it's just saying that you gain two equations, and you're supposed to find y over x. How should we find y over x? Well, you may say, let's find y and find x. Then we can find y over x. Yes, reasonable. But there's a big but here. Let's see what we can do. First, let's simplify. Simplify again. Well, from that, we can conclude 8x is equal to 20y. Then, what is y over x? Y over x is simply 2 over 5, and we're done. We didn't solve for y and x, but rather, we just solved for y over x. And this is what I call to what extent do we solve. we solved it by obtaining what we want, but not obtaining everything. And sometimes in this problem, we can solve for x and y, but sometimes it's just not easily solvable for every single variable, so you have to know when to stop. But there is another meaning to what extent do we solve, which is determining whether something is solvable. For instance, this is a really classic example because the determinant of this quadratic is 4 minus 8, which is -4. So this is not solvable. But this is not the real point. The real point is I want you to look at this problem. This problem, well, there are two variables, only one equation, so you might assume that there exists a y for every possible x. Well, it is not the case. Because suppose x equals 0. You get y squared plus 4y plus 5 is equal to 0. And in this case, the determinant is -4. Again, unsolvable. What happened? Well, if you look more closely to the expression, you notice that this can be simplified to the following expression, right? Then that means since both terms are at least 0, then both are 0 because their sum is exactly 0. That means x equals 1, y equals -2, and this is the unique real solution. So this is a much more surprising discovery in to what extent do we solve, and this is important to keep in mind. Even though both examples are not from AMC12, we will encounter another very interesting problem in lesson 5 when we analyze more advanced inequalities. At this point, we have successfully finished our journey through the pyramid, from the basics to what to solve, then to what extent do we solve. And now it is time we actually tackle difficult problems that comprehend everything and requires your ability to break down the equation carefully through observation, through analysis, and through using what we learned. So the problem statement doesn't really look that intimidating. It's just a very mild looking equation, right? But let me first explain what this means. Suppose x is equal to d plus f, where d is an integer and f is between 1 and 0, where 0f can be equal to 0. We're supposed to find an a such that the sum of all such x is 420. Well, I guess we can first solve for x, right? To solve for x, we need to first solve for d and f. Since we have this equation, we can naturally conclude d times f is equal to a times d plus f squared, which is then equal to a times d squared plus 2adf plus a times f squared. This can be simplified down to a f squared plus 2a minus 1 d f plus a d squared. Now, the reason I'm focusing on f is because f has a clear constraint we can deal with, which is it is between 0 and 1. Okay, now let's just solve for x using the quadratic formula. First, the determinant here is 4a squared d squared minus 4a d squared plus d squared minus 4a squared d squared. These two terms cancel off, so we can conclude it is d squared times 1 minus 4a. This is the determinant. Then we can plug this thing into what we have concluded. So f is equal to 1 minus 2a plus or minus 1 minus 4a over 2a times d, because there's a d from the determinant, and there's also a d from the original coefficient of the first degree term. Now it is high time we analyze which solution do we want. First of all, since the determinant here, this implies that a is less than 1/4. Otherwise, there will be no solution. Since a is less than 1/4, we can then clearly conclude that this term is greater than 2. So just this section of the expression is already greater than 1. And we know f is less than 1, so we must take the negative sign. So we can remove the positive sign over here, and we only need the negative sign. This is our next conclusion. Well, this looks like a mess, so we replace it with k. F then is equal to k times d. Now, let's analyze the constraints a bit further because we're a little stuck. Since a times x squared, each of them is greater than 0 because if x is equal to 0, it just doesn't contribute to the count of 420, so we don't need to consider it. Then that means the left-hand side must also be greater than 0. So we gain stronger constraints because d must be positive and f cannot be 0. These are some better constraints. So now we can solve confidently that since 0 is less than k and kd is less than 1, so we can conclude this is the interval where k lies on. However, remember, k is the constant, so d is the one that is actually changing. To what extent can it change? Well, if d grows smaller, then of course the right interval of k grows larger, so the constraints are going to be looser. But if d grows larger, then at some point it is going to grow that k cannot be between 0 and 1 over d. So assume this maximum is big D. Then that means big D plus 1, 1 over big D plus 1 is lesser or equal to k, and 1 over d is greater than k. In this case, we have successfully represented the entire thing using a surprisingly simple formula. Because we know f is equal to kd, that means x is simply d times k plus 1. And the sum of x is simply k plus 1 times the sum of d, which is k plus 1 times d plus 1 over 2. And we know this is equal to 420. What then is k? Because we know k, we can then solve for a. Well, here it is not clear, because the reason here behind it is that we only know d is an integer. This is all we know. That means solving this thing requires some integer evaluation, and meantime, it must also satisfy this requirement. So k cannot be an arbitrary amount. It must lie between these two values. Well, the first thing we notice is that we can move this divided by 2 over to below k plus 1. Because really we're trying to analyze d. We're trying to analyze the one with a constraint, which is d as an integer. So we can move the other constraints to other things, and we can conclude over here this term is between 1/2 and 1. That means d times d plus 1 is between 420 and 840. That means d is between 20 and 29. Since we know k is an exceptionally small number, because even if we take the smallest possible d, k is still around 1 over 20, so that means the true value of d is going to be closer to 29, because d must be larger since k is very small. So the first thing we can try is d is equal to 28. In this case, solving the equation, we arrive at the conclusion that k is equal to 1 over 29. Let's check if this satisfies this constraint. 29 over 1 is exactly 29 over 1 over 29 is exactly less or equal to k, which is 29. 1 over 29, which is less than 1 over 28. So this constraint is satisfied when d is equal to 28. So since we already know k is equal to 1 over 29, you can plug this back to solve for a. But since there's a square root over here, which is not very friendly for us, why don't we analyze it in another clever little way? Because we know x is equal to d times k plus 1, and then we also do know that the original equation have one-to-one correspondence. This is d, this is f, this is a times d times k plus 1 squared. So a is actually simply d times f over d squared times k plus 1 squared. And ultimately, a is simply equal to k over k plus 1 squared. K is 1 over 29, so the answer is 1 over 29 over 30 over 29 squared. So the result is 29 over 900. And we are done. That is basically the hardest problem in AMC12 algebra. This, in fact, is indeed one of the hardest problems. So what I would like you to do after this video is review the problem-solving process by doing the problem entirely independently on your own again. Just don't try to recite my way of solving, just do it naturally. Just look at the problem, start from what seems reasonable to you, and just step by step try to derive the entire thing. And in case you're a bit mystified, let's just analyze what we did here. Well, first of all, we dissected the constraints. This is a crucial step for us problem solvers. Then we begin by solving a basic equation, which is a quadratic here. This expression is equal to 0. Then again, we dissected some constraints over here so that we arrive at these results. And then we moved on to create yet another expression using the sum of x because we already have sufficient power to express them. And then here, this is the power of what to solve. So you notice that we came to the conclusion of that we're going to try to solve d equals 28 easily because we analyzed how things are growing, like how big is k? And this means this is going to give you a better guess. Well, this is slightly different from what we mentioned about what to solve before, because before we are just analyzing equivalent amounts, but this time we're just looking at the balance of the two sides. The two sides originally is already an equivalent amount, but we're trying to balance it so that it actually stays around equal, so we can actually solve it, even though there are two variables. And then finally, here we ultimately arrived at k equals 1 over 29. Of course, we can plug it back into this expression, but we concluded that this is a bit hard. So this, again, is to what extent do we solve? And we tried to take a simpler version. We went back into the original problem, concluded that a is simply equal to k over k plus 1 squared, which makes the solving process extremely easy. And we are done. This is basically the main part of today's lesson, and the rest is just presenting you the homework for today. So for today, the homework is simply review this problem. This is very important. I really like this problem. And then after that, you are required to solve problem 13 and 14. I would give both problems a difficulty of 3, so don't worry, they aren't too hard. And the last problem is for those who are ready to challenge something tough. This is a level 5 problem. And because this problem is very tricky, I'm going to give it a 5.5. This doesn't mean this problem is harder than the problem we analyzed previously. This is actually a little easier, but the 0.5 here really means that it is tricky. It is really easy to get incorrect. And that is basically that. So in conclusion, we traveled down the entire path of solving equations, ultimately to be able to solve such a hard problem. And also we did a quick preview on basic inequalities and a little bit of preview on the future classes. We'll be talking more about polynomials in the future. We'll also be talking about inequalities, advanced inequalities in the future. So tune in and we're going to have some fun math in the future. I will see you in 2 days. Bye, have fun learning math.